Previously, we have found a necessary and sufficient condition for two polynomials to have a common zero. The problem with that condition is that it's not very useful computationally. So in this video, we want to rephrase this criterion into something more explicit and computable. We claim that the above criterion is equivalent to the following. Suppose f and g are of this forms. Now we can form a matrix in terms of the coefficients of f and g called the Sylvester matrix. The determinant of the Sylvester matrix of f and g is called the resultant of f and g. We claim that f and g have a common root if and only if this resultant is 0. Moreover, we claim that these two propositions are actually equivalent. This one is just a rephrasing of this one. So let us see why that is. Let us illustrate that by an example. What we just said might sound very complicated, but when we work out with a concrete example, you'll see that everything is very simple. So let us try to figure out whether or not these two polynomials have a common root. Well, obviously, in this case, you can compute directly, and you see that they do have a common root. But I want to use this example to illustrate a way of rephrasing this criterion. And at the end, we'll see that the new rephrased criterion is gonna give us that these two polynomials do have a root just as we expect. Alright, so this criterion says that f and g have a root if and only if there exists polynomial r and s of degree less than degree of g and degree of f respectively, such that f times r is equal to s times g. This means that r must be of degree less than 3 and s must be of degree less than 2. So we can assume that r and s have these forms. Now that we know their form, finding r and s is now equivalent to finding their coefficients. And if we think that way, then we can turn this into a linear algebra problem. We can use this equation to create a system of linear equations in the variable ai and bj's. So let us do that. Let us first multiply our r and f. Note that here I intentionally multiply this top term a2x squared with this whole polynomial fx first and put it on the first row. Then on the next row, I multiply a1x with this polynomial fx, and then on the last row I multiply a0 with this polynomial. And the reason I wrote it in that way is so that it's easy to see the following. This polynomial here, the result of multiplying rx with fx, is a polynomial of degree at most 4. For convenience, we want to write it as a vector. In other words, we want to choose a basis for the space of polynomial of degree at most 4. The obvious choice is, of course, x to the 4, x cubed, x squared, x and 1. And in terms of that basis, a polynomial cix to the I can be identified with the vector c4, c3, c2, c1, c0. Now, with respect to that basis, what is the coefficient of this polynomial? Well, its first coefficient is a2 times 1, which is just the dot product of this with this. Now, its next coefficient is a2 times minus 5 plus a1 times 1, which is the dot product of this with this. Next up, the coefficient of x squared is just 6a2 minus 5a1 plus 1a0, and that's just the dot product of this column with this row vector. Do you see the pattern here? Observe that the vector corresponding to this polynomial can be obtained by multiplying this with this matrix. And how do we get this matrix? Well, observe the way that I have arranged these rows. Doesn't this matrix look a lot like the blue coefficients in these rows? And where do these come from? Well, they are the coefficients of f. So to get this matrix, we just write down the coefficient of f. So on the first row, we start from the first column On the second row, we start from the second column. On the third row, we start from the third column, and so on. How many rows do we need? Well, as many rows as the number of this AI. And observe that the number of AIs are exactly equal to the degree of G. So we'll put as many rows as the degree of G. Alright, so let us do the same thing for Sx multiplied with Gx. Let's try to write this in vector form. Actually, let's try to form the matrix first and check that the answer work out. So as we mentioned, we want to write down the coefficients of G. Note that there should be a 0 for coefficient of x squared. So on the first row, we write down the coefficients of z, and starting from the first column, on the second row, we write down the coefficients of z, starting from the second column, and so on. Now, how many rows do we need? Well, as many rows as the number of bi. But the number of bi is equal to the degree of f, which was 2. So we only need 2 rows, and so the matrix will look like this. Let us check that this indeed gives us the coefficient of this polynomial. And again here, I multiply this out in this order intentionally. So I first multiply b1x with this whole polynomial, and then I multiply b0 with this whole polynomial on the second row. Observe that the coefficient of x to the 4 check out. Similarly, the coefficient of x cubed is indeed the dot product of b1, b0 with this column. And as you move on, you see that the coefficient of x squared is indeed the dot product of this column with this vector, and so is the coefficient of x. Alright, so now that we have found Rf and Sg in vector form, we want to use our criterion and set them equal. Thus, we have the following system of equation in terms of Ai and Bj. For convenience, we could move everything to one side. This gives us a homogeneous system of linear equation. And we know exactly when such a system has non-trivial solution. This system has a non-trivial solution if and only if this matrix has 0 determinant. Now this matrix is exactly what we call the Sylvester matrix of f and g. And its determinant is called a resultant of f and g. So we see that f and g have a common 0 if and only if there exists polynomial r and s and so on, and that's if and only if there exists coefficient ai and bj that form the roots of this homogeneous system of linear equation, and that happens if and only if the determinant of this matrix is 0, i.e. if and only if the resultant of f and g is equal to 0. Thus, we have reformulated our criterion into something explicit and computable. To check whether or not two polynomials f and g have a common root, we form the Sylvester matrix of f and g, and then take the determinant, that's the resultant of f and g, and then we check whether or not that's 0. If it's 0, then f and g have a common root. If it's not 0, then they don't. In our case, I explicitly chose f and g so that they have a common 0. So this determinant should be 0. You can verify that by explicit computation. Or you can observe that row A minus row B is going to be equal to row C minus row D. And thus, this matrix has two linearly dependent rows, so it must have 0 determinant. This confirms that our criterion does indeed work. Now you might ask, I said resultant of f and g, why do I write this symbol x here? That's in anticipation of more exciting applications of resultant coming up next.